All right, so today we're going to look at section 7.1, diagonalization of symmetric matrices. Let's just remember, we'll begin by remembering a few things about this diagonalization process. Remember that when I say diagonalize, what I mean is take my matrix A and write it as a product, P, D, P inverse, where D is diagonal. That's what I mean by diagonalize. Also remember that not every matrix is diagonalizable. So what we actually need is we would need to have n eigenvectors that are linearly independent. That's what it takes, right? So if A is n by n, we need to have n different eigenvectors that are linearly independent. Remember our process, right? So the process was to take our eigenvalues, lambda 1, through lambda n and put them on the diagonal matrix. And the matrix P was given by our eigenvectors v1 through vn, which correspond to the eigenvalues lambda 1 through lambda n. And so this is our matrix P, and then multiplied by P inverse. That's the process. So not every single matrix actually is diagonalizable, because we may have a matrix which does not have n distinct linearly independent eigenvectors, in which case this would not be an invertible matrix, so I can't get the P inverse. Now, however, we're going to see that if we use a symmetric matrix, we can always do this, and actually we can even do better than that. All right, so here are the facts about symmetric matrices that make this work. So these are theorems in the textbook and in this section that we're not going to worry about proving right here. But here are the things that are true about symmetric matrices. So if A is symmetric, remember what that means. Right, so that means that A is A transpose. So that means that I have any entries on the diagonal, and then if I flip over the diagonal, I get exactly the same matrix. So there's less information contained in a symmetric matrix, because the stuff below the diagonal is exactly the same as the stuff that's above the diagonal. But here's what's true about symmetric matrices in regards to this diagonalization process. We always have n linearly independent eigenvectors. Which means that it is always diagonalizable. And so this takes some work, but it is true. We're not going to worry about proving it, but this is something that what we're going to do is we're going to spend our time focusing on how we actually will be able to diagonalize a given matrix. We're going to look at examples of diagonalizing a symmetric matrix, and just take this fact as true. Another thing that is true is that if I have two eigenvectors corresponding to different eigenvalues, then the eigenvectors are in fact orthogonal. Right, so the eigenspaces for different eigenvectors or different eigenvalues are orthogonal. So if I have two different eigenvectors that corresponded to two different eigenvalues, then those eigenvectors are perpendicular. And so what that means is that we'll actually be able to, rather than just diagonalize the matrix, when we write down A equals P D P inverse, we'll be able to make the matrix P an orthogonal matrix. So if A is symmetric, we'll be able to write A as P D P inverse, where this is actually orthogonal, because we create the matrix P by listing out the eigenvectors, and we just, while we didn't prove it, it is true that eigenvectors corresponding to distinct eigenvalues are perpendicular, which means that many of the eigenvectors that we use to create P will be orthogonal. We're going to have to see that we're going to have to apply the Gram-Schmidt process in some cases. If I have a single eigenvalue that corresponds to three different eigenvectors, we'll end up getting 3 eigenvectors. They'll be orthogonal to all the other eigenvectors, but we'll have to apply Gram-Schmidt on those 3 that came from the same eigenvalue in order to orthogonalize those. All right, so, but that's our process, and we'll write that down and we'll practice it. So we're going to be able to make this an orthogonal matrix, and this is a diagonal matrix. And so remember that if P is an orthogonal matrix, then P inverse is just P transpose, which is going to make our life a bit easier for lots of situations. P transpose is in general much easier to calculate. We just flip over the diagonal as compared to P inverse. Okay, so let's just look at this process with a bunch of examples. And so here's the phrase we'll use. Orthogonally diagonalize the following matrix. So this is a symmetric matrix. Remember, the 1 and the 1 wouldn't have to match. These could be anything I want. But if I flip over the diagonal, the 5 and the 5 match, so that this is, in fact, a symmetric matrix. So in order to orthogonally diagonalize, we need the eigenvalues, the eigenvectors, and then we'll see what to do after that. All right, so first, let's find the eigenvalues. So step 1, let's find eigenvalues. All right, so we'll do that by looking at A minus lambda I and taking the determinant, as before. All right, so A minus lambda I is 1 minus lambda on the diagonal, 5, 5. And when I take the determinant, I get 1 minus lambda squared minus 25, which is 1 minus 2 lambda plus lambda squared minus 25, which is lambda squared minus 2 lambda minus 24. So let's just remember our original matrix, 1, 5, 5, 1. So this factors as lambda minus 6 and lambda plus 4. So that tells me that lambda is 6 or lambda is negative 4. And those are our 2 eigenvalues for this particular matrix. Our next step in general is to find a basis for each eigenspace. Now, because this was a 2 by 2 matrix and we have 2 different eigenvalues, we're only going to get one eigenvector for each eigenvalue. In general, we have to check and see. Right? If I had a 3 by 3 matrix, I might end up with 2 eigenvalues, and one of those eigenvalues ends up with 2 eigenvectors. So we'll look at examples like that, but we're starting out with something that's simple, where we only have 2 eigenvalues, each of which will correspond to a single eigenvector. So remember what we're really doing here, as we're looking at then A minus lambda I as a system of equations set equal to the 0 vector. Right, so this becomes, in this case, so let's look at lambda equals 6 to start. If lambda is 6, this becomes A minus 6I. But A minus 6 is, so that 6I is minus 5 on the diagonal. On the diagonal, 5's everywhere else. We row reduce this, and it becomes minus 1, 1, 0, and then zeros on the bottom row. This corresponds to negative x1 plus x2 is 0, and x2 is free, which means that x1 is, if I bring this over, negative x1 is negative x2, so x1 is x2 and x2 is free, which means that for lambda equals 6, our eigenvector is the vector x1, x2, which is x2, x2, which corresponds to 1, 1. Right? So 1, 1 times x2. So this is our eigenvector corresponding to lambda equals 6. Now, for lambda equal 4, our other eigenvalue, then we have a minus 4I set equal to 0 becomes minus 3, 5. Oh, so that was lambda equals, sorry, that was actually lambda equals negative 4. Because of how we set up, because of our characteristic equation. So that's actually lambda equals negative 4, which becomes a minus negative 4I, so that's a plus 4, which is 5, 5, 5, 5. This row reduces to 1, 1, 0, 0, and then zeros, which says that x1 plus x2 is 0, and x2 is free. So x1 is negative x2, and x2 is free. So our vector is negative x2, x2, which corresponds to the vector x2 times negative 1, 1. So for lambda equal negative 4, our vector is negative 1, 1. So now we have a basis for each eigenspace. Now, in general, I'll write down the next steps, and we'll apply them to more complicated matrices. They're not going to apply, this next one isn't going to apply in this particular situation. But if an eigenspace is more than one dimensional, so if I have 2 vectors or 3 vectors or 10 vectors that corresponds to a single eigenvalue. So our next step in the process would be this. If an eigenspace has more than one basis element, we need to apply Gram-Schmidt to the basis for that particular eigenspace. Because remember, our goal here is to come up with an orthogonal matrix. So we want every vector to be orthogonal. So that means that when I have a particular basis, the vectors that I get may not be orthogonal, but we can orthogonalize them by using the Gram-Schmidt process. So then we'll look at one like this in the future. We'll look at a few like that in the future. But for now, that's the next step in the process. Remember that an orthogonal matrix is not only a matrix with orthogonal columns. The word orthogonal matrix includes a hidden definition, a hidden requirement that the column vectors also be unit vectors. So we need to normalize each of the eigenvectors that we get. Normalize, and by normalize, I mean, so we're going to take each eigenvector v sub k, and we're going to turn it into vk divided by its length, so that I get unit vectors. And then, so in that case, we can do that for these things, right? So what we're actually going to use is we're going to use 1, 1 divided by the length, which is the square of 1 squared plus 1 squared, which is 2. So we get 1 over the root 2 and 1 over root 2 as our first eigenvector. This one also has a length of 2. So our second eigenvector is going to be minus 1 over root 2, and then 1 over root 2. Remember that scaling a vector doesn't change the fact that it's an eigenvector for corresponding to the right eigenvalue. So this is still an eigenvector for lambda equals 6. This is still an eigenvector for lambda equals minus 4. So our last step in the process is really just to write down P and D. So if we write down P and D, so we're going to write down A is P, D, P inverse. And so let's write down D first. Remember, D is just a diagonal matrix where I put the eigenvalues on the diagonal. So we had 6 and minus 4. and everything else is going to be 0. Since I wrote down 6 first, I have to write down the eigen vector corresponding to 6, which is 1 over root 2, 1 over root 2. And then 4 came in my next column, so I write down the eigenvector corresponding to negative 4. Negative 4 came in the next column. So we get negative 1 over root 2, 1 over root 2. Also keep in mind that these are perpendicular, right? So if I take 1, 1 and I dot it with minus 1, 1, then I get negative 1 plus 1, which is 0. So I had two different eigenvectors corresponding to different eigenvalues, and they were already orthogonal. And so that's great, and that's always true if I start with a symmetric matrix. So if I start with a symmetric matrix, and I get eigenvectors for different eigenvalues, they're already orthogonal. So after scaling, they stay orthogonal, and this becomes a matrix P, which is now an orthogonal matrix. Because the vectors are perpendicular, and we've normalized them to make them unit vectors. Finally, P inverse, but remember P inverse in this case is P transpose because it's an orthogonal matrix. So P inverse is just 1 over root 2, and then if I transpose, this comes up here, 1 over root 2, and then minus 1 over root 2, 1 over root 2. All right, so let's take a second and let's just make sure that after we multiply these things all together, we really do get back to A.
So I have used the Mathematica program to input our matrices P and D, and we'll use this to make sure that PD, P inverse is in fact our matrix A that we started with. I started by defining P. Remember our syntax, you don't really have to be able to reproduce this, but this is the syntax for defining a matrix, and I've put it into our matrix form, which is nice, so it looks like it's supposed to look like. And I'm not allowed to actually use D because that letter is reserved for something special in Mathematica, but I called the next matrix DG for diagonal. And again, this was our matrix created out of the eigenvalues from the matrix A. And also here, notice that if I take the inverse of P, so if we calculate P inverse, we get this matrix down here, which is exactly the transpose of the matrix P. So this is something that we noticed should be true for any orthogonal matrix. That is a matrix with orthogonal columns that are unit vectors, and we find that that's actually true in this case, which is good because it's got to be true in every case. And finally, I calculated P times our diagonal matrix times the inverse of P, and put it back into matrix form, and we do find the matrix 1, 5, 5, 1, which was the symmetric matrix A that we began with, which confirms that all of our calculations were correct, and we've been able to orthogonally diagonalize our symmetric matrix A.
Okay, so we'll look at another one. This one's a bit more complicated. It's a 3 by 3 matrix. I'm going to give you the eigenvalues already for this one because just to save us some time, in general, you have to know how to calculate the eigenvalues by getting the characteristic equation, but it's a bit more complicated with a 3 by 3 matrix, and in order to save us that time and focus on the diagonalization process, I'm going to give you these eigenvalues of 7 and minus 2. All right, so keep in mind that this is a symmetric matrix because if I flip across the diagonal, I get minus 2, 4, 4, and 2, 2. So it's a symmetric matrix, so we will be able to orthogonally diagonalize. Right, so 1, find the eigenvalues. Well, I gave them to you. All right, we're done with that. So that's lambda equals 7 and lambda equals minus 2. 2, we need to find a basis for each eigenspace. So let's do that. So we need to start with one of the eigenvalues. Let's look at lambda equals 7. So we're looking at a minus 7I set equal to 0, which becomes 3 minus 7, which is negative 4. 6 minus 7 is minus 1. 3 minus 7 is minus 4. And then nothing else changes. And then we're setting this equal to to 0. And we'll row reduce this matrix. We should be able to actually see what happens right here already, but feel free to use your calculators to make sure that you like what you get and you're happy with it. So I'm just going to row reduce this on my calculator. And this is what I get. So notice, for lambda equals 7, we have 2 free variables. x2 and x3 are free. This means that we're going to end up getting 2 eigenvectors corresponding to lambda equals 7. So this particular eigenspace is 2-dimensional, and we will actually have something to do in the next step. All right, so this becomes x1 is negative 1/2 x2 plus x3, and x2 and x3 are free. So if x2 and x3 are free, that means that the vector, the eigenvector, will be minus 1/2 x2 plus x3, x2, x3, which is x2 times minus 1/2, 1, 0, plus x3 times 1, 0, 1. So our eigenspace, our basis for the eigenspace corresponding to lambda equals 7 is 2-dimensional, and I have 2 vectors. I get 2 vectors out of it. So I have lambda equals 7. Let's put that over here. Lambda equals 7 gets me 2 vectors. V1 is minus 1/2, 1, 0. V2 is 1, 0, 1. We also have to do our other eigenvalue, minus 2. So if we look at lambda equals minus 2, we're looking at a minus 2i set equal to 0. So that's plus 2, which becomes 5, 8, 5, and nothing else changes. Set equal to 0. And again, we're looking to row reduce. And if we do that, what we get is 1, 0, 0, 0, 1, 0, 1, 1/2, 0, 0, 0, 0. And now we only get 1 free variable. x3 is the only free variable, which means we'll get 1 eigenvector for lambda equals minus 2, which is great because we already had 2, so we knew that the most we could get is 1 more. This becomes x1 is negative x2. Negative x3. x2 is negative 1/2 x3, and x3 is free. So we get negative x3, negative 1/2 x3, and then x3, which is x3 times negative 1, negative 1/2, 1. So lambda equals minus 2 gets me the eigenvector v3 minus 1, minus 1/2, 1. Now, just a couple of things to point out here. Notice that if I would take v1 and v3 and dot them, I get 1/2, negative 1/2, and 0. So v1 is perpendicular to v3. Right, so also notice that v2 dot v3 is negative 1, 0, and 1, which makes 0. So v2 is perpendicular to v3. So our eigenvectors corresponding to distinct eigenvalues are already perpendicular. That's great. However, v1 is not perpendicular to v2, because if I dot these, I get negative 1/2, 0, and 0, right? So So this one is not perpendicular to V2. So when we go through this process, we get some things that are orthogonal, the things that correspond to distinct eigenvalues, but we still have to orthogonalize within a particular eigenspace. So the stuff corresponding to lambda equals 7, we got two eigenvectors. They are not necessarily going to be orthogonal. This is where we have to go to step 3 and apply Gram-Schmidt. And in this case, the only eigenspace we have to look at is the lambda equals 7 eigenspace, because the lambda equals -2 only had one vector in it. But remember that when applying the Gram-Schmidt process, it's often easier to work with vectors that don't have fractions in it, and we can scale our eigenvectors without changing the fact that they are eigenvectors. So what we're actually going to do here, when we apply Gram-Schmidt, is actually use, rather than this vector, we're going to scale it up to not have any fractions. So if I multiply everything by 2, this becomes -1, 2, 0, a vector that doesn't have any fractions in it, and we'll still use V2, 1, 0, 1, because that already doesn't have any fractions. And so we're going to apply Gram-Schmidt to these two vectors. Now when we apply Gram-Schmidt, remember what we're doing is we're taking a set of vectors which spans a subspace, in this case the eigenspace corresponding to lambda equals 7, and we need to find a basis which is an orthogonal basis rather than just any basis, because these vectors were not perpendicular. The way to do that is to keep u1 just equal to v1. So we're not going to change our vector, our first vector at all, -1, 2, 0. And then we need to adjust any remaining vectors. This is a pretty simple case because we just have one further vector to deal with. So remember, the idea here is that if you forget what to do, just draw our favorite picture. So we've got, what we're doing here is we're going to adjust this vector. So this is our v1, this is our v2. We're thinking about projecting. This is the projection of v2 onto v1, which means that this is the vector that we want, because that's the perpendicular one, which still spans the same thing. If this is the projection, what we actually then have up here is v2 minus the projection. So v2 onto v1. And so our u2 is that vector there. v2 minus the projection of v2 onto v1. And so let's just calculate that with our v1 and our v2 that we have right here. So that is 101 minus projection of v2 onto v1 is v2 dot v1, which makes -1 plus 0 plus 0 over v1 dot itself, which is 1 plus 4 plus 0. Again, this is why we scaled v1 up, because having fractions in there just makes this calculation more complicated. And then we have to multiply by v1, which is -1, 2, 0. And so that makes 101 minus, so that's -1 over 5, which makes plus 1/5, minus 1, 2, 0. If we simplify this, we get 1 minus 1/5, we get 0 plus 2/5, and we get 1, which is 4/5, 2/5, 1. And again, we might as well scale. There's no reason to include a complicated vector which has fractions. Why don't we just scale this up by multiplying by 5, and if we do that, we get 4, 2, 5. Right? So our u1
let's just summarize what we've got. So our U1 was the scaled V1, which was minus 1, 2, 0. And our U2 is 4, 2, 5. Notice that U1 dot U2 is in fact 0 because I get minus 4 plus 0. So now we have created a perpendicular set of vectors which still spans the eigenspace corresponding to lambda equals 7. So the vectors that we're using at this point are no longer these two vectors, but instead minus 1, 2, 0, and 4, 2, 5. And we're still using V3 that's down here. This is now an orthogonal set of vectors. Remember, the next step in our process is to normalize. So step 4, normalize, that is make things unit vectors. If I make things unit vectors, well, the length of this is square root of 1 squared plus 2 squared, which is the square root of 5. So I have 1 over root 5 times minus 1, 2, 0, which is minus 1 over root 5, 2 over root 5, 0. The length of this is 1 over the square root of 16 plus 4 plus 25, which is the square root of 45 multiplied by the vector 4, 2, 5. Square root of 45 is 9. 45 is 9 times 5, so that's 3 root 5. So that's 1 over 3 root 5, all multiplied by this stuff. So that's 4 over 3 root 5, 2 over 3 root 5, and 5 over 3 root 5. We can scale this one again if we want to, but we don't have to at this point because we're still calculating the length. We'll get the same thing in the end, whether we scale this up or not. The length of this one is the square root of 1 squared plus 1/4 plus 1. And so that's 2 1/4, which is 9/4, and the square root of 9/4 is 3/2. So that's 2/3 times our original vector. So if I multiply by 2/3, I get minus 2/3, minus 1/3, and 2/3. And these are the three vectors that we end up with using in our diagonalization process. Okay, so that was step 4. Step 5, we're just going to create P and create D. Let's keep what we found. So we're going to be using the vectors minus 1 over root 5, 2 over root 5, 0, and also the vector 4, there's no negative there, 4 over 3 root 5, 2 over 3 root 5, 5 over 3 root 5. And for lambda equals negative 2, our normalized vector is minus 2/3, minus 1/3, 2/3. So the final step in the process, create P and D. Remember that D is just a diagonal matrix created out of our eigenvalues. In this case, that's 7, 7, and minus 2. Everything else is 0. And P is the matrix where I just take my eigenvectors and put them right underneath the corresponding eigenvalue. So this will be minus 1 over root 5, 2 over root 5, 0, 4 over 3 root 5, 2 over 3 root 5, 5 over 3 root 5, and then our final eigenvector, minus 2/3, minus 1/3, 2/3. And this is P and D, And what we're going to do next is we'll move over to Mathematica just to check, in fact, that P, D, P inverse is, in fact, A. Now, one other point before we do that, there's no good reason why this eigenvector should have gone first. In fact, if we would have switched the order of these two, it's still going to work because they both correspond to lambda equals 7. In fact, we could have put -2 up here and then 7, 7. We could have put these in any order as long as we match the order of our eigenvectors up according to our eigenvalues when we create these matrices. All right, so after we look at this to make sure that this is in fact true and look at some rearranging, then we're going to be done with this section, and we'll see you next time for our very last discussion of a section in the book. So in this Mathematica program, I have stored the matrices that we need for this particular example. The first is our diagonal matrix. I've stored it as DG because D is a reserved symbol in Mathematica. But we see the matrix 7, 7, minus 2 on the diagonal. I also stored as P the matrix that we came up with, and it looks slightly different down here just because the only thing that's different is this very bottom entry, but it simplified this entry so that we actually had a radical in the top, not in the denominator. But it is the same thing, and I actually entered it as √5/3, which is what we actually calculated up here anyway. But so we've got D, we've got P, and I just simply multiplied P, D, times the inverse of P to see what we get. And after doing so, I put it into the form that we're used to for matrices. We come up with our beginning matrix A that we started with. And second, just to emphasize the point that I made at the very end, if I put these eigenvectors in a different order, and so that's what I did here. I used P1, which is really just a different order of the eigenvectors. Notice that I just switched the order of column 1 and column 2, because both of those eigenvectors corresponded to lambda equals 7. So that should be just as fine. After I do that, and then I multiply by P, D, P inverse, we still end up getting the matrix A back. So it doesn't matter what order we put these in as long as the eigenvectors are directly underneath the eigenvalue that they belong to. And that's what we got from this section. I will see you next time.